So hello everyone, my name's Keith Gallent from RMS Reliability. We work in vibration, but in the rotating equipment domain. So we also look at reliability as a whole and condition monitoring within a number of different industries: petrochemical, oil and gas, pharmaceuticals, anywhere where there's rotating plant and equipment. So I've got a couple of subjects I'm going to talk about today, but I'm going to centre it around a new technology called motion amplification. We're going to talk about equipment failure. 80% of all equipment failure is random in nature. An unusual figure when we think about how we treat our equipment in terms of maintenance. We're going to look at the technology of motion amplification. It's a very new development. It's just a step change in vibration, and it's a real game changer for how we measure vibration. And then also looking at the proactive approach and some examples and case studies that we've got. So typically, you probably hear a lot about preventative maintenance and calendar-based maintenance as being a buzzword at the moment in many different industries. But some time ago in the 40s, it was established during the war. The RAF established that this was causing more failures on their machines than it was if they were to just run them to failure. So human induced problems come from planned and preventative tasks. So if we think about that figure, 80%, that comes from a number of studies that was done later in time, the 70s, 80s and 90s, where 80% keep coming back for random failures. 80% of all failures are random. So how do you plan for random? If your maintenance strategy is that you're going to change it at this date, but you've got a random time in between there. So just a little example of that. This is a chart of a life scatter chart from a bearing manufacturer, a very popular bearing manufacturer, where we've got 30 bearings all run in the same conditions, and these are the failure rates that we see, and you can see that randomness in there. So it's quite interesting to think about that when you think in terms of I'm buying in a piece of equipment from an OEM that tells me it's going to run for 3,000 hours, and at that point, 3,000 hours, that's when you need to do your maintenance. So you can just have that warm, cuddly feeling that it's going to be fine and the plant will run. But remember, there's that 80% chance that it will fail. So we can plan for that, and we can actually also have management strategies in place that avoid that. You used a nice phrase earlier about buying out noise. Is it along those lines? Sorry, can you remind me of that phrase? Buy quiet. Buy quiet. Yeah, I like that. So we ask our customers to buy reliability. Look at the whole asset life cycle. If we can tell our suppliers a list of specifications of how the machine should arrive, how it should be installed and commissioned, and acceptance criteria that increases reliability over its lifetime, then obviously we reduce the life cycle cost of that machine. So moving on, the technology we're looking at to help along with that, the commissioning and identifying problems early on, and also during the design phase, is called motion amplification. And we use a standard grayscale camera, and at each pixel on the camera we can measure displacement values. What we can see on the left-hand side, and in the videos you're going to see in the next few slides, is a standard video. That's a video playing, and it's just got no amplification. Where we've measured vibration at each point, we can take that value and say, let's see that times up to 50. And that's what you see on the right-hand side. It's the same video, just this one has the vibration amplified. So how are we using that in practice? We can go to a brand new machine that's just been installed and identify an issue before it's commissioned and allowed to be handed over to maintenance. On the left-hand side is the video, it's playing, but on the right-hand side, the dramatic things you can see, instantly your eyes are drawn to where the base is really poor quality, it's weak anyway, and it's got these looseness parts on it, and also there's a seal failure straight away. Why is that seal failure there? It's pretty obvious, because this machine is allowed to move this amount in operation. So we also found very quickly, in 6 weeks, we had bearing defects on these machines. So at this stage, using this technology early on during the commissioning phase, we can avoid problems in the future. Just to show you a before and after, so there's that same shot, just with all 3 machines in. They're all bad. At 20 millimeters per second in velocity. We then have the rectification. So we've now got a really good sturdy base for that machine and a reduction in vibration levels at 94% below. It's down to 1.2 millimeters per second, which is much more acceptable. So of course, to kind of bring that into the noise domain as well, I've got a noise example as well. It's not something we do on a regular basis, but obviously you can use this technology in the same way to visualize noise. In fact, you talked about a camera earlier, a noise camera. I've never heard of that before, and I thought, wow, this is very similar. So on this bit of plant, it was a dairy that had bought a refrigeration package, and this is a package that came just off the shelf, designed as it is, goes in situ, and off you go. But they had environmental noise complaints of a village nearby. When you're next to the machine, it was over 100 dB. We were asked to just investigate the problem with the camera. So we identified, obviously on the base, it's acting like a drum skin. What's really good about this technology, you can just draw a box anywhere on there and it will give you a spectrum and a waveform, so you can do your analysis. So we'd identified these 2 frequencies, and these were related to the vane pass on the compressor. What it really comes down to is poor design, poor acceptance criteria. Buying a package that is just built for everybody. There's no reason why you can't specify to your supplier that you want a particular set of specification for your plant. So this machine is designed to arrive at any plant and just start running. But it doesn't take the asset itself, where it's sited, and the plant that it's sited in into consideration. So the solution, we gave the data over, and the solution they came up with was to add mass and stiffness using a very thick piece of steel under the bed. This is running next to the one I've just shown you. And they've added stiffness along the base, which has massively reduced the noise. It's massively reduced the noise. However, there's still an inherent issue where these anti-vibration pads are generally used on these type of machines for reduction in vibration levels on suspended floors, but we're on a solid concrete base. Why would we want to try and dampen that using those pads when we can build a good base for that machine, throw away all the steel work and have it nice and solid on a good concrete base? So try and think of it as like, encourage people to think, if you went to hospital for a brain injury and they gave you Calpol, that's really not going to help. We want to be treated as individuals, don't we? And that's the way we should look at our machines. So bit of a segue back to safety as well here with some fans. I know it's a passion of yours. It's also a little bit of passion of mine for fan safety. We often see a lack of understanding around the safety aspects on fans. So if you think, many fans run between 900 and 3,000 RPM. So that when that fan, if it fails and it lets go, as we call it, it can fly off at between 100 and 300 mile an hour when it flies off. In this instance, we've got a fan that's about 1.5 metre in diameter, the blade that comes off. So if the whole thing had come, it would have been a lot larger. And you can see these poor blokes running for the lives, no doubt, as it flies off. Now the story behind that is, well, we do condition monitoring to monitor condition of the plant for reliability, for vibration problems. And that allows us to look at bearing problems and do preventative tasks then on condition. However, if we're not given that type of equipment that we know is safety critical, enough kind of understanding and appreciation for the level of damage it can cause, they kind of fall into the background, those ideas of preventing failures. Because if we were to treat it as it is, as an individual, that it's got that capacity to cause damage, we can use the condition monitoring to monitor the dangerous aspect of it, which is that ability to let go and fly out. And we do that through sensors that are mounted in the correct place. In that previous fan, we weren't allowed to mount the sensors on the bearings where the fan is mounted. So when that fan let go, there was no monitoring on it. And that's what we see often in industry, that fans like this run without any monitoring on them whatsoever. When we do see monitoring on them, often we see this problem. So you can shout out the answer, but where do you think the degree of movement is greatest on this fan?
Not vertically.
Not vertically, no. So we've got gravity pushing down. If vibration increases on the fan, it's most likely to be in the vertical domain, so on that plane. So it's no good being vertical for a start. Where else? Where's the bearings on this fan? Any idea?
Either end of that shaft.
Yeah, so here there's a bearing behind the guard, and here's another bearing behind the guard. So the fan in here, ideally, we want to put this sensor horizontally mounted onto the bearing. We're as close as possible to the bearing and the shaft where the vibration is going to be most easily sensed. If we're measuring it here, it's the wrong plane and it's away from the source of vibration. We'll actually only just trip the machine after it's flown off. So this is, again, I come back to lack of understanding and appreciation, because this is an installation on an oil rig by a well-known protection system manufacturer. So, coming back to motion amplification, we use that technology to convey the message, to demonstrate as a communication tool what it actually looks like, what the problem's like. So on the left, again, this is the normal video, and on the right, this is the amplified one. And this is a 0.5 megawatt fan that's running. It's running with a bearing looseness, so it's running close to its failure mode. And you can see the whole structure is vibrating. And here's the fan behind here, and you can see the bearing massively moving around. So I'm able to then show this video, instead of using the traditional graphs, and the spectrum and the graphs in orbit plot there, instead of using those which are just numbers and go straight over most people's heads, I can show them a video and they can see the damage that's being caused, and it helps them to get an appreciation and to act quickly. So just to recap, 80% of all equipment failure is totally random. And an interesting read for you if you're trying to challenge culture in your business is the ISO 55000 standard of asset management. We want to improve reliability throughout the whole asset life cycle, from the design phase, commissioning, the running phase, and at the decommissioning. We want to be trying to do as best as we can, most responsible we can. We can use a variety of technologies. There is vibration analysis, thermal imaging, ultrasound and oil analysis. And there are other techniques out there that can help us monitor condition for the life cycle. And we're trying to treat machines as individuals, understand the failure modes and effects of that machine on its own. And then we can mitigate for their failures. So, thank you.